Next up, we're thinking about some examples of existence and uniqueness for initial value problems and boundary value problems. So we're going to stick to the same differential equation each time, x double prime plus 16x equal to 0. That's a second order linear differential equation. And if I think about like x of 0 equals x1 and x prime of 0 equals x2, or even some generic x value that it takes on, it can be, or sorry, t value that it takes on, it can be any initial condition. But our functions that we care about are 1, 16, and 0. So that would be called a2 equals 1, a1 equals 16, and g equals 0. So those are always continuous. And a2 is never 0, it's 1. So because of that, there is a unique solution for any values we pick of t0, x1, x2. And that solution exists on the interval negative infinity to infinity. But if we go ahead and change this just a little bit, we'll start to see that boundary value problems don't follow those same rules. And I just need to note real quick that the solution to this differential equation right here is going to be x equal to c1 cosine of 4t plus c2 cosine of 4t. And the way we're going to see that the boundary value problem doesn't have solutions is just going to be by trying to find those c's for given problems. So, pause here if you needed to write down some more stuff before I change the page. But our next example is going to use that same initial condition. But now we're going to consider a, sorry, I'm so used to writing initial value problems for you all that I wrote a derivative, but it's going to be a boundary value problem. We're going to think about x falling between 0 and pi over 2, and x has to take on value 0 at either of those points. So I'm going to have that I need, for x of 0 equals 0, I need 0 to be equal to that c1 cosine of 4 times 0 plus c2 sine of 4 times 0. And for x of pi over 2 equals 0, I'll need 0 equals c1 cosine of 4 pi over 2 plus c2 sine of 4 pi over 2. And just based on what sine cosine are, I know that's going to be c1 times 1 plus c2 times 0 up top, or just c1. And then down below, c1 times 1 plus c2 times 0, because these are becoming 2 pi. 4 over 2 is 2. And 0 and 2 pi give you the same answers all the time. So I just get c1 again. So when I try to find what c1 and c2 are, I know that c1 is equal to 0. But c2 could be anything. So for example, x equal 0 cosine 4t, but then like 4 sine 4t would be a solution. c2 equals 4 is fine. Sorry, I don't know why I accidentally moved the page like that. But also x equal to 4,000 sine 4t would also be fine. So x is not going to be a unique solution. So even though the initial value problem theorem guaranteed the existence of a unique solution, the boundary value problem doesn't necessarily have a unique solution. I could find infinitely many right here. We could also see an example with different conditions. Let's do x of 0 equals 0 and x of pi over 8 is equal to 0. And in this case, my two conditions give me that I need to have 0 either when I plug in 0 like before, so I know that that one ends in C1 equals 0 because I did it up above right here. But then for this new one, x of pi over 8 equals 0, I'll have C1 cosine of 4 pi over 8 plus C2 sine of 4 pi over 8. And 4 pi over 8 just becomes pi over 2 for both those. So pi over 2 ends up being this part of your unit circle. So I'm going to get C1 times 0 plus C2 times 1 just gives me C2. So my solution here is that C1 equals 0 and C2 equals 0. So there is exactly one solution. Unfortunately, that solution is just x equals 0. So it is a unique solution. We'd also consider it a trivial solution because 0 is going to be a solution to lots of things. And then pause here if you're still writing down those examples, but I'm going to go ahead and do the third case. If you're used to like solving algebraic equations, you might already know what's coming. But I don't have to write example again. Same differential equation. Now let's think about if x of 0 equals 0 and x of pi over 2 is equal to 1. In this case, we're going to have, I'll write it down below like I was. 0 is equal to C1 cosine of 4 times 0 plus C2 sine of 4 times 0. We've never changed this condition. It's just C1 times 1 plus C2 times 0 gives us C1. So we still need C1 equal to 0. Oops. But now this second condition right here gives me C1 cosine of 4 times pi over 2 plus C2 sine of 4 pi over 2. And that 4 pi over 2 just becomes 2 pi. And I'm sorry, I copied that down wrong. It's x of pi over 2 equals 1. So I should have a 1 right here, not a 0. Make sure that you fix that if you were copying it down as I wrote it. And since it's 2 pi, we've gone back around the unit circle, so we still get C1 times 1 plus C2 times 0 is just C1. But now I have the requirement that C1 equals 0 from the first condition, C1 equals 1 from the second condition. That can't happen. So since C1 can't be both 0 and 1, there actually isn't a solution to this boundary value problem. So what we've seen from all these examples is the boundary value problems can have infinitely many solutions, no solutions, or exactly one solution, which is what you learn is true of systems of algebraic equations, which is kind of what we get when we're trying to solve one of these problems. And what's interesting is that's true even if the corresponding initial value problem had uniqueness.